also Research Associate Professor of Computer Science at USC. And I'll talk about our work on detecting DDoS attacks and developing this solution called AMON-SENSS. This is joint work with my students, Raja Tandon and Piteyu Chorusetikul from USC, and our colleague, Mihalis Galitsis from Merit Networks. So before I start, I'll give you just a background. I know I talked about AMON-SENSS maybe 4 or 5 years ago at this conference. That was the beginning of our project. So we had about 5 years of development. It started as a DHS-sponsored effort to work on distributed solutions to DDoS attacks. And at that time, we didn't really focus on detection. We focused on how networks could collaborate together to handle DDoS attacks. But as we went into the project, we realized that there are no good open source solutions for DDoS detection, and we needed it for the project, and so we started developing our own, and we invested several years into development and testing, so we believe now it's ready for use by other networks. So let me see, do I need to point this, or? I'm not sure why. I'm not sure why it's not going forward. It was doing it a moment ago when I was testing, but now it's not. Yeah, sure, but okay, while we wait. The goals were to develop something that is an open source research solution, explainable and deterministic and ready to use by others, and something that is highly deployable, so something that works offline, it's not in path of traffic, it works with different formats of traffic. It produces actionable network level signatures that you could then feed into your firewall to handle those attacks. Okay, awesome. Let me try now. Okay, great. And so our open source solution is at this link given here, and the nice thing is if you search for it on Google, you can find it easily, so you don't really have to remember the link. I'll talk a little bit about DDoS attack detection challenge. So for the background, I worked in DDoS area for 2 decades. And my PhD was on this topic, and then I ended up doing more research on that when I became faculty, and I kind of worked on DDoS on and off, looking at different types of attacks and different deployment challenges and attacking the problem from many different sides. So overall, we all had DDoS problem for decades. It's hard to detect these attacks because some of them are fairly obvious. They just create a deluge of traffic at the target, but some are more subtle and they attack maybe a single host and not the whole network. And so at the network level, if you're trying to deploy something that would detect these attacks, it's hard because overall volume at the network level is small, even though the target host is overwhelmed. Or the target could be an application, so you have either even smaller volume that is hitting that application, but still the application goes offline. So that's one challenge. The other challenge is that if you're trying some thresholding approach to detect attacks at the ISP level, there are many different targets, they have different capacities, so it's hard to set up those thresholds correctly. Some attacks are also short or intermittent. You can detect those, but it does you no good because you don't have time to mitigate them. They will stop in a few minutes. And so you want to kind of balance that with the level of alerts that you're generating that your operators have to handle. And then some attacks are launched by numerous sources, so you could use that as a signal that the attack is going on if you see the increase of sources going to a given target. But one, it might be hard to track this in a scalable manner because there are many potential targets and many sources, so you will need a lot of memory to track this. And also some attacks can spoof, so you will, you might see only one source if they are spoofing only that one source. And some attacks are port scans, there are port scans that also use multiple sources, so you might mistake them for attacks if you're going off that signal. There are many research solutions for DDoS detection, and they all focus on detecting the onset of the attack and not so much on developing a useful signature. So they might detect the onset and maybe the target. Some of them may list the sources that are involved in the attack, and again, that's of limited usefulness because you really want something that you can scalably deploy in the network to filter out the traffic. If you're getting a list of sources, these sources could be spoofed, they could be changing over time, and also there may be too many sources and your switches have only limited rule space. Also some research solutions use machine learning, and that's great for robustness, but it's also not very good with regard to explainability. You're getting some detections and some rules that are hard to interpret for humans. On the other hand, we have commercial solutions. They are fairly opaque. They don't tell us how they are detecting attacks and how they are filtering them. So we had to go and look into their brochures and their ads to draw some conclusions about how they work, and they seem to mostly work based on thresholding. So when you subscribe to one of these commercial solutions, you have a chance to set up the threshold, how much your network can handle, and then once the traffic goes over this threshold, they will raise an alert, and they will divert traffic to their scrubbers for mitigation. The scrubbers use some signatures to scrub traffic. They don't really tell you what these are and how good they are, so you kind of have to trust them that they're doing the right thing, but you don't have a way to independently evaluate if they are dropping some legitimate traffic along with the attack and if they are dropping enough of the attack. And so also for the signatures that involved content, they require DPI. So this is something that sites that have large scrubbers can do, like these commercial defense systems, but it's not something that is deployable in your network if you want like a homegrown DDoS detection and mitigation solution. And so we wanted to develop something that sits in between this and in this research gap. We wanted to develop something that would be open source, give you actionable network level signatures, be scalable and deployable by any network. I'll talk a little bit about DDoS attack signatures. To develop good signatures, you need to have some notion of how legitimate traffic looks like in absence of attacks. And that's fairly hard to do in a scalable manner because there are many potential targets, and if you track traffic to all of them at peacetime, you'll have a lot of different traffic records. And most of them will not be useful to you because only some targets will be hit by attacks. And so the challenge here is how to develop these signatures in a way that is scalable and to develop them with some small processing cost and small memory cost. And we would ideally like to develop them so that when we detect the attack, at that time when we raise the alert, we already have a ready signature, and I'll tell you how we do that. So with all this in mind, our design goals for AMON-SENSS were to develop something, again, that is deployable and scalable. You could run it in an ISP that serves millions of customers, with some guaranteed memory and CPU cost, and it would produce alerts that are at least as accurate as a commercial defense. And at the time that it produces alerts, it would also give you a network level signature that you could deploy. And to do that, we are using very deterministic set of algorithms. We're not using any machine learning. We made that choice for deployability so that you can run this at any hardware. It doesn't have to be fancy hardware with GPUs. And also for explainability, so that when you get those rules and you get those detections and something's not right, you can understand why you're missing something or why you're getting some false positives. So I'll talk a little bit about internals of AMON-SENSS. I said that we want to limit the memory cost, and we do that through binning. You can think of binning as hashing. So you take some features of a flow and you pass them through a hash function, and out comes an index, and that index points you to the bin where you will store these statistics. In this figure, I'm actually illustrating multiple arrays of bins. So an array of bin bins is shown here in different color. You have yellow ones and gray ones that are shown interchangeably. And then you have some green bins that I highlighted. These are the bins that will be updated for this sample flow. Each array of bins uses one specific feature of the flow. We have 16 arrays, so we use 16 different features. For example, the first array uses the local IP. So this is the IP, we call it local IP because it's in the network that we're trying to protect. And I believe the fifth one is using the combination of the local IP and the foreign port. And we concatenate them together, we hash that, and then we find the index of the bin where those statistics will be updated. And so because we use hashing or binning, there is the chance of false positives or false negatives. I'll tell you in a few slides how we deal with those. But that is the secret sauce that limits the memory cost. And so regardless if you have a few thousands or a few millions of hosts that you're protecting, your memory cost stays the same. It's based on the number of bins that you have selected to use. And we also focus on service ports. We focus on traffic going to and from the local hosts and the traffic going to and from the service ports. And this is a design decision, again, that is made for scalability and to reduce false positives. This is something that is fairly easy to change because this is an open source tool. So if you believe that there's a high chance of you being attacked from high numbered ports going to high-numbered ports, so neither is a service port in a flow. You could just, change 2 lines of code and get AMON-SENSS to look at traffic to those ports as well. So in this example, I'm showing a sample flow going from 1234 port 80 to 5678, some high-numbered port, and it has reset flags on that flow. And the 5678 is our local IP. That's the IP we're trying to protect, one of many. And so we are hashing different fields of this flow and finding the entrance, the index of a bin. And you can see that some bin arrays will not be updated. For example, the bin array that has the combination of local IP and local port will not be updated because the local port here is high-numbered port, so we're not going to do anything to update this kind of statistics. So the statistics we keep track of are fairly simple. They are surplus and asymmetry as defined with regard to traffic going to the local addresses. So surplus is the difference between bytes received and bytes sent for that local address. You can think of this as when there is a DOS attack, the traffic increases to local hosts, and this is what we are trying to detect with surplus. Asymmetry is the ratio between the packets received and the packets sent. And asymmetry helps us track the ability of the host that is receiving traffic, of the local host, to handle that traffic. Because most of the traffic that is cooperative and consensual is two-directional. And we keep both the historical and the instantaneous values of these statistics. We will use them in anomaly detection. We update the statistics on each flow or each packet, and then we roll back if the anomaly is detected. So our anomaly detection approach is fairly simple. It's a standard approach called CUSUM, and it looks for persistent increase or persistent decrease in a given quantity over time. We require both surplus and asymmetry to be anomalous in order to say there is anomaly in this bin and we should start tracking it. And then after we track it for a while and there is this persistent anomaly, then we will signal the onset of the attack. We want the anomaly to last for a given time because we want to make sure we don't signal an onset of the attack for attacks that are very short, or some anomalies are fairly intermittent and are not due to attacks but due to some fluctuation in the network. And this delay is a configurable parameter. We require both surplus and asymmetry to be anomalous, because if the surplus is anomalous but the symmetry is not, that can just be large file transfer. So asymmetry being normal tells us that the local prefix or host, they can handle it. It's okay. This is within their ability to handle this traffic. And then the asymmetry could be high, but the surplus could be low. That happens in case of port scans. And so in that case, again, we don't want to raise the alert because a port scan is not a DOS attack. And so on this next slide, I'm illustrating one case of attacks. So this is the top graph shows the surplus and the bottom shows the symmetry, and we see the blue line showing these quantities over time. X-axis is the time. And we see the yellow show the range of the historical values. So you can see that there are cases where surplus goes over the historical range. It's anomalous, but the asymmetry does not, and so we won't signal an attack. There are also cases here highlighted in gray when both asymmetry and surplus are anomalous, but it's only for a short time, so we won't signal the attack again. And then there are two cases highlighted in red when the surplus and asymmetry are both abnormal, and this anomaly lasts for some amount of time. You can think of seconds. And then we will signal an alert because we now have met all the criteria for the alert. So I'll talk a little bit about signature generation. We wanted to do this proactive signature generation so that when the anomaly first shows in the bin, we start tracking and generating candidate signatures. And when the anomaly has lasted for enough time and we are ready to export the alert, we also have the signature to export. To do that, we are generating candidate signatures all the time when there is some anomaly in the bin. So when the flow is updated, the bin, and we detect the anomaly, that flow that contributed to the anomalous detection, we are taking its fields and generating candidate signatures. And we generate 7 different types of candidate signatures looking at the combinations of the local IP, foreign IP, the local port, the foreign port, and the TCP flags. So for every flow that contributes to the anomaly will have those 7 signature candidates generated. Now you might wonder what happens, how do we bound this memory cost, because for each bin, there are thousands of flows that potentially are anomalous and going into this bin, and each has 7 candidate signatures. So we use the algorithm called Boyer-Moore. It's a very simple but powerful algorithm that helps us on each update of the signature figure out if that is the dominant signature in the bin, meaning that signature for this flow of this type represents 50% of the traffic in that bin, or more. And so that is the signature that will be kept. So at any point in time, we only have 7 winning signatures that are stored for that bin. And then when it's time to export the alert, when we are sure that there is an attack going on, then we look at these 7 candidates again automatically, we process them, and we find the signature that covers a large portion of the anomaly in the bin, so explains the large portion of the asymmetry. In our case, it's 75%, but that again is a configurable parameter. And then if there are multiple signatures that meet this criteria, we will select the most specific one. And selecting the most specific one makes sure that you are limiting the false traffic drops, right? The collateral damage that might occur. So I'll talk a little bit about alert generation. AMON-SENSS is quite verbose, even though we take good care not to generate many false positive alerts, but it's verbose because it will generate multiple alerts for the same attack. And that's okay. We actually post-process these alerts so that what the operator sees is much more manageable. And we want to have this many alerts because we want to also pick up on the attacks that affect only one bin array, so there are only one specific type of the attacks. So why do we have multiple alerts? We have multiple bin arrays, so that contributes to multiple alerts for a given attack, because the attack might create anomalies in multiple ways. It might send a lot of traffic to a given local host, and also the traffic is, the attack is reflector attack, so the traffic is coming from a given foreign port, so it will generate anomaly in these two bin arrays. We also use multiple bin layers, and we use them to handle false positives. I mentioned that because we use hashing, just like any hashing approach, it is likely that we will have false positives because we are cramming a lot of different flows into one little confined space, right? And so we are using multiple bin layers. A bin layer is one of these, let's see if I can go back. A bin layer is one of these structures that I'm showing here. We're using multiple of them with different hash functions. And so the approach here is similar to Bloom filters. They also use multiple hash functions to reduce the number of false positives and store a lot of data in a limited space. And so this figure illustrates how then we go from thousands of alerts to a small number like 5 or 10 alerts. We do that by aggregating the alerts for a given time period for a given target. And then we also prune those alerts that have a small number of votes. Votes are those raw alerts that we're aggregating. So if we have a small number of raw alerts that we're aggregating over time, that might mean that this attack is intermittent or very short. And then we also require that the alert is present in all bin layers. So that gets rid of some false positives that might occur in one layer but not in all of them. And so in the end, we take what comes out and then we show it to the operator. And then we export it again into a text file that can be either, the operator can review it and manually take those suggested signatures and put into the firewall, or they can automate this and feed it into the firewall. So I'll talk a little bit about the evaluation. We were very fortunate to strike up a partnership with Front Range Gigapop, which is the regional optical network in Midwest that serves academic and research institutions and some government and some local small businesses. And we got from them 37 days of traffic from 2020 that was anonymized net flow. And they also run NetScout, which is Arbor solution, commercial solution for DDoS detection. They gave us those alerts as well, so we had something to compare to. And those alerts were also anonymized. Each alert shows the start and stop of the attack as Arbor. NetScout detected it, the type of the attack, and the target. So we could compare if we're detecting the same things, if we're detecting something they are not, and so on. And so we compared to NetScout, and we also ran FastNetMon, which is another open source solution that is, there is a commercial version and then there is the open source version. And both NetScout and FastNetMon use thresholding technology to detect alerts. So we calibrated on a few days of traffic to learn the thresholds, and then we use those thresholds for detection. We also will share these data sets. We are working with Front Range Gigapop to go, to draft the memorandum of understanding and go through the approval process, but we're very close to having this done, and we'll share it through our ClassNet project. If you search for ClassNet USC, you will find our project page, and there will be the link to those data sets, hopefully in a month or so. We needed to establish ground truth for our evaluation because we wanted to compare to those two competing approaches. And to establish ground truth, we used the approaches that are listed in these papers that I'm citing here. The approach is actually fairly simple. It only focuses on reflector attacks, but these are the majority of attacks that we have in our data set. And it tracks the traffic to all local addresses, so each of them separately, from every service port, and then it will say there is an attack if there is more than 100 megabits per traffic going per second going to a given local IP from at least 10 different sources. And so we use this approach to establish the ground truth. It's shown here in the third column. So I'm showing all the three data sets separately, and the yellow row is showing AMON-SENSS performance. I'm showing the true positives, which ideally should be the same as the ground truth for an ideal defense. I'm showing the false positives, the false detections, and then the false negatives. These are missed detections. These are attacks that were not detected by the solution. F1 score is the measure that combines the false positives, true positives, and false negatives, and closer to 1 is better. And then I'm showing the delay in detection compared to the ground truth. And so you can see that AMON-SENSS does the best out of these three solutions. It has the smallest false positives and false negatives, best F1 score, and it has half to 1/3 of the delay of other solutions. We also looked at the quality of signatures we generate, and we looked at it two ways. We looked at the ground truth detections and derived signatures from these ground truth detections, and then we would compare it to signatures produced by each solution. And we would say that we have a full match if there were, say, several types of attacks in the ground truth, and they were all detected by the given solution, AMON-SENSS, NetScout, or FastNetMon. We would say we have partial match if there were multiple types of attacks, but only some were detected by the solution. And you can see that AMON-SENSS does very well here. Actually, AMON-SENSS and NetScout are comparable on this measure. The other measure that we looked at was how well are these signatures filtering attacks, and are they filtering any legitimate traffic, which is a tricky thing to measure because we don't know with absolute certainty that some traffic is legitimate or not in our data sets. But we did our best. We took the ground truth again, and we used it to label each flow as legitimate or attack, and then we looked what will be dropped during the attack given the signature and given the time when the alert was raised. And so you can see, I'm showing the amount of attack traffic that is filtered, percentage, sorry, of attack traffic that is filtered. And I'm showing the precision. Precision is the percentage of filtered traffic that is actually attacked. So the ideal is 100%. And you can see that AMON-SENSS does very well here, much better than other defenses. NetScout and FastNetMon lag behind because they're not dropping as much attack traffic, and the reason is that most attacks are fairly short, and if you remember, NetScout and FastNetMon had much higher detection delay, so by the time they detect the attack, it's almost halfway through. So with regard to operational performance, AMON-SENSS works faster than real time if you're doing sampled net flow. And in our case, on our machine, which is maybe 10-year-old server, dual Xeon, it was processing 6 to 24 hours of traffic within 1 hour. And this is something that is fairly dependent on not just your hardware, but also the number of bins that you're supporting, which is configurable. If you use smaller number, you'll get faster operation, but maybe you'll miss some attacks. So this is something that, you can use default values, but you can also try to calibrate and play with it a little to see if you will get better performance for the same, and lower cost. I said we work with different types of traffic, so we can work with NetFlow, PCAP flow tools, Flowride, which is a custom type format of traffic that CSU has produced, and we can also work with streaming PCAP, and we are testing whether we can work with streaming NF-dump. We should be able to, but we might need a few more lines of code. We have limited memory footprint, and you can limit the CPU footprint. So CPU footprint pretty much for us comes from unzipping the traces because we were working with traces stored on disk and then with using NFDump. I have a few videos. I'm not sure how we are on time. I think we have, do we have like 10 or 15 minutes? Okay, so I'm going to play the first one and maybe the second one.
So there I will demonstrate how to install AMON-SENSS. First, do a Google search for AMON-SENSS and that will take you to the GitHub repository. At the repository there are releases. I recommend downloading one of the releases instead of the whole source code because the release is much smaller. I'll take the latest release and I'll download it to a new virtual machine. Now I'll extract it. And now I'm going to run configure and make. So the configure fails because I don't have the C++ compiler. So I'm going to have to install that. Okay, and I'll try the configure again. This time it fails because I don't have libpcap, so I need to install that too. Okay, and then we'll try configure again. And this time it works, then we'll run make. Okay, and now we have AMON-SENSS in the home directory. And if we run make install, it will be installed into the USR local bin.
Okay, so hopefully this convinces you that the installation process is not too painful. If you have a standard Linux machine, it should be fairly smooth. The next video shows how to run AMON-SENSS, so I'll play that as well because it's useful, and then we'll skip on the tuning part. I can pause that online.
I will demonstrate how to run AMON-SENSS. I'm now on another machine that has datasets with the tags. I'm in the AMON-SENSS directory and I'm first going to run autoconfig. And it will ask me about a few parameters. It is safe to leave these parameters by default. So I'm going to just accept the default values. Okay, now the configuration has been completed. Before I can run AMON-SENSS, I have to also put the prefixes that I want to protect into local prefs.txt. And I have done that here. So you can see that there are a lot of prefixes. They are /24, but you can put another size of prefix and the code will interpret it correctly. Currently, the code works only with IPv4 prefixes. And AMON-SENSS can read from a file, a folder, or an interface. It can read streaming traffic or traffic that is already recorded in a file. And the code will now run for a while. If you look at the as.out, it will give a fairly verbose output of the files that are being processed, but not so much about what's being detected. The detections go into file alerts.txt, which is currently empty. It is waiting for the alerts to occur. So we'll wait for a while. We can now use read alerts to read the generated alerts in human readable form. And you can see that there is a number of alerts. Number of votes shows how often this alert has been generated, and higher numbers have more significance. And you can see, for example, that this alert has very high number of votes, it has high rate, and there are several candidate signatures. It's up to the operator to choose which signatures to implement.
Okay. Okay, I think it's still maybe hard for you to see that, but I'll put it on the web page and so you can see it on your screen. I'll put it on the AMON-SENSS GitHub web page. We'll skip this one. Hopefully we'll skip this one. Okay, so thank you for attending this talk. Here is the project link and my contact. I wanted to highlight that we would really love to see more networks try to use AMON-SENSS. And I wanted to pledge that I'm here to provide user support to whoever wants to try it, using either Zoom or email or both as many times as you need it. I know that the pain of using a new tool is learning how to use it and learning how to calibrate it, but we've put a lot of effort in this, and we want to go beyond just having a research paper. We want it actually to be useful to people. So if you decide to use it, reach out, and I'll be happy to help you with any, any challenges you might encounter. Thanks.
Hello. Hey, so you mentioned the bucketing and the aggregations. You mentioned aggregating based on port. Do you also do like the protocol, the IP protocol? Okay. And I guess my main question would be surrounding like time buckets. Do you aggregate based on time bucket, or how do you store historical values? Because I know you mentioned you're comparing the anomalous value to historical values. So how do you store that and compare?
Right, so we have the configurable parameter that is the observation interval. Right now, I believe it's 1 second, the default value, and so every time interval we will look at the, what's anomalous and what's not anomalous. We will use to update the historical values. And then we will, again, on each update, whenever a flow or a packet causes an update to the bin, we will do the instantaneous comparison of the statistics in the bin to the historical profile. And we do that because we don't want to limit ourselves to detect attacks after, say, a second or a few seconds. We want to detect them as soon as possible.
Okay, thank you. And I guess can I ask a second question? Anyone else want to go? Okay, yeah. I'll ask a second question. So you mentioned that you, I guess, print the alerts in a flat text file. Is that the only export methodology, or is there any like structured export?
Right.
Options?
So. Yeah, so we are open to different formats. Right now it's in flat text file, and then we use it and crunch it to different ways. One is what I showed here, which is for human consumption. It tells you the UTC time and the local time and, signatures that you might want to implement. And then the other is kind of more machine-readable format that gives you something similar, but in a one line that is easily parsable. And we are open, so if there's another format that works for you, we'd be happy to do that as well.
Okay, great. Thanks.
Yeah, you're welcome.
I think that was my questions.
For configurable, what is your suggested number of bins that one should run, and will configuring more bins help with false positives?
Yeah, so number of bins is dependent on the size of your network. So for FRGP, there were, I don't know off the top of my head, but there were like thousands of /24 prefixes that we were monitoring, so potentially, millions and millions of hosts. And so for them, because that was the biggest data set we had access to, we experimented with different number of bins. And bins in hundreds were not doing so well as bins in thousands. So right now, our recommended value is something around 3,000 bins. We also went up to like 65,000 bins just to see how well this would work. And the benefits are really tapering off. So once you go over maybe 10,000 for this particular data set, you really don't see much difference. Actually, beyond our recommended value of 3,000, we use like a prime number, so that as you're hashing, you have a lower chance to favor some bins over others. But if you go above the 3,000 and some, then you really see like small benefits. Maybe you're dropping like one more false positive as you double the size and so on, but then you hit the plateau. Yeah. You're welcome.
Great. Any more? Oh, all right. Thank you very much.
Okay. Thanks.